going to present you historical, not because I'm a historical person, not because I only am located in the past, sure, but because I know quite a lot about history of mathematics. Yeah, that's all of my name. Can you hear me? No. Better? Better? Like that? Okay. So, now the previous. There are two notions which go together. So we have previous history. One is extension, and the other is variation. We get a little try of variation. What is that? Actually, if I say that it goes back to the 1950, for Baker of Almos, who was a mathematician in the United States of Hungarian origin, this wouldn't be true. I mean, the most important paper was on him, but the notion, at least the notion of extension, and the notion of dilation, is much more longer, much more older. So what are these? To think of those, you have to have two Hilbert spaces. One is the initial one. The other is, people give it different name. Some people say that this is the exit space. This is the terminology of MG prime. And the relation between these two spaces should be like that, which is a set-theoretical relation, but this is too little. We have to assume that this isometry, this is isometry, means one of them, the smaller, is isometrically, that's important, included in the larger space. So if we have a constellation like that, we may think of both extension and dilations. The first thing is to write K, decompose rather K as an orthogonal sum of H and H per the orthogonal complement. This is natural. So if we have it done, we may explain these two notions in a very simple way. Namely, except these two, we have to have two operators, say A and B. Whatever, they may be bounded, unbounded, it's not appropriate, it doesn't matter. So, according to this decomposition, we may decompose the operator B as a matrix. So we have B1, 1, B1, 2, B2, 1, B2, 2. These are operators. It's very clear what it means when the operators are bounded. If they are not bounded, then there is a little work which has to adjust the situation to the truth. And this is on the other, this is in the large space K. In the smaller space A, we have H, we have still this small operator A. It has to be a relation, this is B, between B and A. So there are two possibilities as we see. One possibility is if we have B1, 1 equal A and B2, 1 equals 0, then the matrix looks like this. Here is whatever, here is another whatever, and here is a 0, and we say that it is extension. This matrix is an extension of operators. Well, this operator, written as a matrix, is an extension of the smaller operator. That's clear, because if we apply this matrix to a column vector, say, then only the first, this element counts. So this is extension. What is dilation? That's a little bit more difficult thing. We want to write A as A whatever, another whatever, and one more. If we apply this matrix to a vector which is of the form 0 and something on the first coordinate, then we get AX and 0, and for that we have to project what we got to the first coordinate to get the dilation, means A is equal to B, restricted to the smaller space. So there's a difference. The one relationship between, I hate it. Not extensions and dilations. The one relationship between these is that any extension is a dilation. The other important relationship is that if we have an extension, what about the adjunct operator? And it turns out that the adjunct is a dilation of the adjunct larger space. These are the two relations. Okay. So I explained the notions, and now about the historical development. Actually, the first dilation result. Well, let me start with dilations first. The first dilation result was a result by Gaston Julia, a man who was mentioned in Gazier's talk. And it says something like that if we have an operator of less or equal than 1, then we may build another operator, and this happens in space H. Then in the space H plus H, we may build another operator, actually a matrix, which looks like this. T is here, T star is here, and here is something, if I am right, T star T, and here is 1 minus T, T you start or the other way, maybe it's some minus here or the anti-diagonal. This reminds the simplest unitary operator in 2 dimensions when you have sines and cosines, okay? Then, let me say that way. The relevant picture to that is like this. You imagine this as a space H, so you have another space H, and which makes in total space 2-dimensional picture, which is of the direct sum of 2. And if you have a contraction in this smaller space, let me put 1 here, then the contraction sends vector 1 to some number which is to the left of it as a contraction. So in order to get to make it unitary, we go out of the space. We need one space more, 1 dimension more. Means that we make a rotation, so move on the circle, and this is nothing but the projection of that. The angle is referred to this number alpha. So this is the idea of dilation. You have to go out of the space to enlarge the space, in that case by the same dimension, and you got the dilation. So this is unitary, and we have the formula Pu the restriction to H. This is Julia. Okay? And it has some advantages. For instance, in framing you may apply it. But it has also from the very beginning some disadvantages. So it's not algebraic. Means that if you want to build an algebra over those, then you cannot apply this matricial definition to build an algebra in the larger space. For instance, A squared, T squared gives you another matrix, which is not a square of the initial one. So the question was, how to avoid it? In other words, we come to so-called power dilations. Power dilations. Power is a noun that's not someone's name. Dilation. And what is that? The idea was to make for this operator T in H to find U, which is unitary, sometimes isometry is nothing, in a larger space cage in such a way that all the non-negative powers are just projections of powers of the same operator, which means that this is an algebraic structure because it goes as well for sums. If we build an algebra on the left-hand side, we may get it on the right-hand side as well. So this is power. The first result was in 1953. By Bella, so I'm almost Hungarian now, Szekefalvi, not sure. And he proved that every contraction has a power unitary dilation. And since then, the word power is dropped. Because by dilation, we mean power dilations. And his proof was matricial. He pulled up a matrix, infinite dimensional. You cannot go in the way as Julian did. Was, the dimension of the dilation space. It was twice as much as the dimension of the initial space. Now it's in any case, even if you start with one-dimensional space, you will get an infinite dimension. That's unavoidable. So this new mathematician. And then in 5 years later, another result of Beas appeared. It was, he put this dilation result into the framework of some algebraic construction which was rather universal. Universal in the sense that it includes any, but most of the known constructions in those times. It includes, and people are not aware of that, I'm campaigning each time when I am somewhere attending a conference abroad. This theorem includes, for instance, just to say a nickname for personal so-called GNS construction, which is a minor thing, but it also includes Stein's. Actually, it is equivalent to Stein's, precisely, logically equivalent. You may one of them by using the other by no other means, almost. So this is remarkable also because it contains other results. It also contains extensions. So a couple of words on extensions. Actually, this is about old theory, it goes back to from and the theory is like that. You have a symmetric operator. Just to remind, this is an operator which makes this thing x as y for x is y's in the domain of S, that's symmetric. And you have a notion of self-adjoint operator, which means that precisely that S is self-adjoint with S and a star constant. Every symmetric is self-adjoint, not the other way. Self-adjoint operators are of great importance because they have spectral theorem. Spectral theorem is a bit light. Therefore, a question whether or not you may, if you have a self-adjoint, you may put a star here, which you replace by S, you see that this self-adjoint satisfies the same inequality. Is what I said, self-adjoints are symmetric. So the question is whether you may extend which says symmetric operators to self-adjoint. And from when I did it, not really in the sense I just explained, but he did it in a more simpler case. When the extension is in the same space, so that is the most natural extension. And he characterized, it was one time ago, all those symmetric operators which have extension in the same space. They are precisely those which have so-called equal efficiency indices, and those things are very, one may calculate that. That's very advantageous. But there is quite a lot of operators which are out of the game of von Neumann. So we have to do with those symmetric operators. Then another name is related to this. That's Naimark. Naimark invented was in the world time, the end of the world time, you know, some mathematicians were still active, depending on the country they worked in. He proved a remarkable result that every symmetric operator has the Serva-Chern extension. Means, if it doesn't have it in the same space like von Neumann, it does in a larger space. And he proved even more that those which are von Neumann, which has extension in smaller space, they also fit in with his extension. So we have extensions of symmetric operators. That's one. Another thing, which is somehow much simpler, is we have ten zapas puszki, który jest na to muszę... Space, which means that this is almost unitary operator. The only difference is that it's not object, it's not subject. So the range may be not the full space. The range of the full space. Unitary. So anyway, if you have this kind of configuration, isometry, then you may extend the whole, the curve H to the curve K, and you, this is unitary. This is an old thing which goes back to Neumann and Benn, a statistician, Swedish statistician. So we have to say very carefully, because it's not American. Well, so you combine these two, you get an extension. And this is another kind of extension, you extend the space. And that is a very simple, so there's a very simple illustration. We have L2 space in the circle, and we have something which is called arc space. Circle. There is nothing else but the analytic part. And we have multiplication by the independent variable, because the independent variable is the simple analytic function. Because we are still in representation you can see here. So this picture shows you, tells you that you may extend this multiplication, which is by the way in this geometry, to a unitary operator in this empty space. And there is something which goes along with this, namely, let's say unitary operator. But this operator is not everything. So this picture tells you that this operator could, whatever, is extendable to a unitary. And this is something which was called at the time cycle. A normal operator always has spectral representation. So this is a very welcome class of operators. Subnormal, those which are extendable to normal, are also interesting because at least we may inherit an analytic part of the spectral representation from the expression. Because the integral, spectral integral to normal operator gives you a picture on the, for instance, for any continuous function. Functional package. If the function is analytic, then you make the results of your subnormal. That's the very technical package. Very subnormal. So it turns out that subnormality fits in that 55. Also. So this is one side of the historical. The other side is that there was a, was a strong core analysis. Break. Oh, I'm at the beginning of my talk.
Okay, so that's not
maybe 2 minutes. Sure. So what do I want to say? No, I wanted to tell my personal story. So we can do that.
Okay, so let's now have 10 minutes break and count your eggs.
So this was half an hour. And then I get another hour.